Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
So I wanted to kind of recap some work that I mentioned on the Casper stand-up a week or so back. And I thought it would be a good topic for the RCast. It's technical, but it's really fun technical stuff. Let me quickly bring up the slides. So what inspired me to talk about this at this time is a class that Nima Arkani Ahmed gave at Harvard Physics this past fall. The lecture series is called Space-Time, Quantum Mechanics, and Positivity. So he sort of takes the approach of calculating scattering amplitudes for particle interaction in a situation where he eschews virtual particles. So everything is on shell. And he shows that the positive Grassmannian is directly connected to the amplituhedron and gives you these really nice, crisp calculations for these scattering amplitudes. So it's a really interesting perspective. And he arrives at a kind of graph rewrite formalism for calculating these things. That's very similar to the kinds of things that I contemplate when I think about models of computation, and especially things like the row calculus. So that was kind of on my mind, and I remembered this work I'd done about a decade ago, in which I was showing that you can get more direct geometric encodings into the process algebraic setting. At one point we talked about knots as processes. So that kind of topological information is really not the same as geometric information. Geometric information is a little bit more detailed. Topologies don't preserve things like distances. Now, I'm not gonna go as far as encoding Euclidean-like geometries, but I am gonna go after projective geometries. And and in particular, I'll limit the scope of the discussion to encoding, finite projective geometries like the Fano plane, which is sort of the simplest example. The point here is, while Ladle as an algorithm allows us to look at generating type systems for a wide variety of algebras and calculi, and so it could be applied to something that like Clifford algebras that already encodes geometric information. This is different, right? This is, can I get geometric information directly encoded into the process algebraic setting? So let me just stop there and make sure that what I've said makes sense to you guys.
Yeah, so this is reminiscent of the Erlangen program. What can you say about like the connections, similarities, dissimilarities?
Let's remind our listeners what the Erlangen program is.
Yeah, so my recollection of the Erlangen program is to have some sort of algebraic classification for geometries in terms of group theory and I think projective geometry.
Yeah, right. I'm glad you said that, because it loops back around to the mention of Ladle. So yeah, if I can come up with a decent process algebraic encoding for a variety of geometries or geometric spaces, then I can employ the type system for the particular process algebraic framework that I'm using, and that becomes a classification mechanism. So it fits perfectly with the intent of the Erlangen program.
Okay, so it would be like a type classification for geometries?
That's right. Yeah.
Oh, that's cool.
Yeah, exactly.
So what is the motivation for incorporating geometry?
I can tell you sort of what my immediate motivation was at the time. So at the time I was thinking about this, I had been talking to a lot of biologists. It was clear to me that the kind of work that Shapiro and Aviv and Cardelli were doing was important in the sense of capturing certain aspects of the dynamical information in these cell signaling networks and other kinds of biological networks. But that at the end of the day, a lot of the information really needed to rely upon geometric information. So a lot of the dynamics of these networks rely upon geometric information, and protein folding is the best example. So it was really, at that time, it wasn't like I was seriously attempting to go after the protein folding problem or any really serious geometric problem. I just wanted to see for myself, can I, in a reasonable fashion, encode geometric information in this setting? Yeah. And the answer is a resounding yes. And so, there's another aspect to this conversation. So a point that Bob Kuka makes when he talks about the graphical language that he develops for quantum mechanics. So he points out that in the using the standard presentations of quantum mechanics, it took people 60 years to spot quantum teleportation. Whereas when you use the graphical presentation that he and Alex Kissinger developed, you can spot quantum teleportation immediately.
Yeah.
Right. And so there's something about different presentations that make certain things really jump out at you, and not just that they jump out, but they open up different kinds of questions. By the same token, if you look at the sort of considerations that Einstein and Hilbert were putting together when they were thinking about general relativity, they weren't thinking about compositionality, and they weren't thinking about bisimulation-like things for dynamical systems, asking when different representations might yield the same dynamical system. And they weren't thinking about type-based classification. But it turns out that all of those things are immediately present. The thing that's a real stumbling block for Einstein and Hilbert is not a static geometry, but a dynamic geometry, right? It takes Einstein a long time to be able to get this recursive relationship between the stress energy tensor, which is giving you the distribution of matter and energy, and the metric tensor, which is telling you how space is warped.
Is that what you mean by a dynamic geometry, just this interplay between the stress energy tensor and the metric tensor?
Well, that's very physical, right? That's,
yeah.
Right, but what I mean is geometries that evolve over time.
Okay.
So Euclid does not discuss the evolution of Euclidean geometry, for example, into a hyperbolic geometry. Mm-hmm. Riemann does not discuss the evolution of a hyperbolic geometry to a projective geometry. However, once we go through this presentation, what you'll see is that this idea of an evolving geometry is right in your face. It jumps out immediately. So that's why this is fun to talk about, because the presentation makes different questions immediately apparent. Mm-hmm. So the phonoplane is defined by some points and lines. So there are 7 points and 7 lines, and every point is on 3 lines, and every line contains 3 points. And so if you try to draw that in Euclidean geometry, you will fail. Because you have to break the parallel line thing to do it. So in particular, if in the diagram, if you look at L7, line 7, it doesn't look anything like what we think of as a Euclidean line. My idea, which was directly related to a lot of things that I've been thinking about in terms of knots as processes, is that lines are going to be processes. And so the phonoplane is going to be a parallel composition of lines, but the points are going to be sets of red X's. There are going to be ways in which the lines can interact. And so if you look at this diagram, I've color coded it. So if you look on the diagram, L1 and L3 and L4 should be able to interact at point 1. And that's exactly what we see. The red parallel, the par end in each of those lines represents a potential interaction.
Yeah, that's cool.
I mean, for the listener, the slides will be up and available on the website, but it should be straightforward to follow the encoding. But now in the encoding, what I've done is to make it abstract in the continuation of the interaction. So L1 has a par end, which is interact on X13, wait for something on X13, call that something that you get Y13, and then become P13. And that's in summation with a similar kind of thing on X14. And the interesting point is that if you make that par end go back to itself, then the phonoplane will remain stable. This encoding will remain stable.
If you make what go back to itself?
So if you make P13 basically be that sum. So you do a recursion, right? Everywhere you have a continuation, you have to have a recursion. Similarly, for the outputs, those would have to be banged in order for the thing to be stable.
What do you mean by stable?
Otherwise, it will evolve to something that isn't the phonoplane.
Oh, yes.
Yeah, you're saying like if you allow, you go one step, make a reduction or something, that it'll go back to the phonoplane only if you make these continuations. So in the expression that you're looking at, particularly P13 and P14, do they both have to be that choice expression?
They both have to be that choice expression.
Okay, yeah, that makes sense, right?
Yeah, exactly. Immediately, what this raises is the possibility that they don't go back to that.
Yeah,
that they go to something else, right? And this then raises all these wonderful different distinctions. Okay, so you could imagine that you have a notion of continuity, where whatever the evolution is, you always get to something that's a geometry. So you have to say what a geometry is. So for example, it's a set of points and lines with coincidence relations for the points and the lines.
Yeah.
So you always get to something that is a geometry. Now we can easily imagine that it evolves to something that isn't a geometry, where you don't respect the coincidence relations, for example.
So you're talking about whether or not you can encode an arbitrary parallel of processes into one of these
geometry.
And when are you saying that's possible?
So it's possible whenever you have a collection of par ends that look like lines and a collection of red X's that match up the points and respect the coincidence relations, as they do here.
So if they don't interact, they don't have potential for interaction. They're just like parallel lines.
Yeah, for example, that's exactly right. Isolation is akin to parallel in Euclidean space. Yeah, that's right.
I was going to ask, what determines input versus output here? Is it just to make the potential for interaction match up?
That's right. There are many different encodings that will respect the same coincidence relations.
Oh, okay.
Yeah, and in fact, there's something interesting here, which is that I do want to point out. I have used mixed summation, so we can actually look at different kinds of lines, right? So there are lines where you've got sort of uniform summation, and you can distinguish the lines that have only input or output from lines that have mixed sums, like L7 has a mixed sum. And to the best of my knowledge. I can't remember exactly, but I'm fairly certain that you can prove that you can't encode the phonoplane without mixed summation. I think it's a fairly straightforward proof. I don't remember exactly the steps that I took to get there, but I'm fairly certain that I concluded that you have to have mixed summation. And that says something very interesting, right? Because Palamadisi's theorem is that you can't have a par-preserving encoding of mixed summation down to asynchrony, or down to something that is only input guarded or non-mixed. So there's an expressiveness jump that is necessary to encode the phonoplane. That's really quite interesting. So these kinds of observations that you can make with the process encoding, that one plus the one, Christian, that you observed, which is that there's some kind of analog between parallelism and interaction or isolation. So you can begin to classify the lines by the types of interaction they support. You can see that different geometries are going to demand certain kinds of expressiveness characteristics within the calculus. And so there's lots of opportunity here, I think, for exploration, along with the fact that you can now start reasoning about geometry using bisimulation, which is an extremely powerful proof technique.
I was trying to picture how an interaction here would cause this picture to evolve. For example, if L1 communicated with L3 on the red, P1 red X, what would happen to the graph?
So let's say that you choose the X13, Q13 output, and therefore you choose the X13, Y13, P13 input. If P13 doesn't put back what you got, you no longer have an L1 or an L3.
Well, you still have like pieces of them somehow.
You have pieces of them, but you don't have the line.
Yeah. So
right?
that whole bottom left chunk of the triangle disappears?
Disappears, exactly.
Okay.
Yeah. We talked about stability, right? So stability is where, when you evolve, you get back to the phonoplane. And then we talked about continuity, where when you evolve, you get back to a geometry. And then you can have this other notion, and this is something that people have actually contemplated when they're thinking about string theory. You can have evolutions which take you away from anything that is geometric, and then eventually it comes back to something that's geometric. So these are kind of miraculous states. Like, so you go through this period where water turns into wine, and then you come back to the normal world again. That's also really interesting to me, right? So this is the equivalent of tears, right? In string theory, they've contemplated the possibility of tears in space-time.
Yeah, I was going to say, that sounds an awful lot like a singularity.
Yeah, that's exactly right. Thank you. You can contemplate these geometries that support is probably a strong word, but where you might be able to reason about a notion of singularity. This is another interesting fact of this particular presentation. From my perspective, what it shows is that we've barely scratched the surface of what we can do with these kinds of computational techniques. This shows, in a way that you could teach to high school students, some of the power of the process calculating that's just waiting to be explored. We haven't really thought about at all what we can do with these gadgets.
Yeah.
They're super, super powerful. And we really know very, very little about them. There's a lot more that we can encode in this way, but in particular, the things that are important that I keep coming back to. The thing is computationally complete, so it has a certain minimal level of expressiveness. The thing is compositional, and this is really, really important because it means that you can reason about things in chunks, as opposed to having to consider the whole system all at once, which is one of the biggest challenges for physics and for a lot of classical mathematics. It's not compositional, and so you have to have these sort of global or God's eye views, which make problem solving very, very hard, and also make physical theories less testable.
Do you have any writings about the general form of this encoding?
I make mention of it in lots of different papers, but I don't think I ever wrote a paper specifically focusing on that encoding of graphs. And that's largely because I developed the toggle theory, which is specific to graphs. But one thing that could be done is to show that every toggle expression has a encoding in row calculus, for example. That would be a way to expose these graph encoding techniques. It's also interesting to contemplate, how does this change when we start talking about infinite geometries? The thing that makes this tractable is, of course, the finiteness of the Fano plane, 7 points, 7 lines. It's easy to write down, but once you start getting these infinitary structures, how does that change the expressiveness power of the process calculus?
Yeah.
One observation that I wanted to make here, because I didn't notice this the first time I watched this stuff during the Casper stand-up, is that so like intuitively lines 1, 2, and 3 are really similar somehow, right? Because they all lie on the outside of the triangle, this picture, and their encodings are all very similar, no mixed summations. The lines that kind of all intersect at that midpoint, so line 4, 5, and 6, also all have very similar encodings, like with one mixed summation. And then line 7, the circle that connects all of those midpoints, also has a different encoding, and they're all mixed summation. So I just thought that was interesting that you've kind of like captured somehow properties of the lines themselves, and the fact that they are similar with other lines in the encoding. I thought that was really interesting.
That was very much on my mind when I was constructing the encoding, to try to make sure that the shape of the encoding respected what seemed to be going on in the geometry. Right. I confess that I didn't explore a number of alternative encodings to see if this kind of distinction always shows up, because it was so obvious that the encoding should respect this distinction. Right. I picked an encoding that made that as evident as possible. But this is where I would hope that the type system would start to get really interesting, so that we could pick those kinds of phenomena out, at the type level, and then and then we would have a lens. We could, maybe that we still have the outer triangle, but the inner stuff starts to get a little more interesting or intricate. And so then you could have types that describe the boundary, but are less distinct about what's going on in the middle, and so then you get lots of geometries, or the other way around, types that describe the interior but not the boundary. Anyway, I just think to me it's pretty and it's cool, and it says that we really don't know how much more we can say with the process algebraic stuff. I mean, certainly we can say stuff about protocols, we can say stuff about topology, and we can say stuff about geometry. But how far we can go with that, I think I'm really hoping to inspire, another generation of folks to go and investigate these problems. Art is long, life is short.
Is there any connection between this and the theory of graphs language you were talking about a while ago?
Yeah. Well, that's what I was saying. When I call it toggle theory of graphs.
Oh yes, yeah.
So yes, there is, right. So, and that's what I was saying is I could take a toggle expression, which will give you a graph.
Yeah.
And encode it this way in this technique. So since that's really a theory, you could say that these are models of the theory. You could actually develop a whole interesting theory model structure that way. In fact, it might be interesting to apply ladle to that. Yeah, so you could apply ladle to the theory, you could apply ladle to the model. Then you have to have a morphism from the types you get for the theory to the types you get for the model. That would be an interesting thing to take a look at as well.
Yeah, definitely.
So how are things going? I have to ask before we sign off, how are things going with the work that you reported on last time, Christian? Any further developments?
Going well. It's all going well. I'm just trying to pump out this paper, or it might be a series of papers And the probably the most interesting question is going to be exactly how much we can express using this method. I have figured out how to do recursion in this setting because basically you can take a theory of the row calculus. You're sending each base type or sort there to the lattice of subfunctors of its representable. So for each sort in the theory, you're getting a hiding algebra. So you're basically like painting the original theory into the category of hiding algebras. In particular, they are categories. They're Cartesian closed posets, and they have some other nice stuff. And so in particular, the result that you get over there is more than just your original theory. It has adjoints to certain operations. In particular, you can consider like endofunctors on one of the hiding algebras. So for example, if you had a process with a free variable of sort process, this is a functor from the lattice of processes back to itself, because it takes in a process and plugs it into that free variable. For any endofunctor, you can always take the initial algebra of that endofunctor. And that's what gives you, for any process with a free variable, when you want to say the mu x to do the recursion, you're forming the initial algebra of that endofunctor.
Oh, I see. I understand. Typically, you want to do recursion, though, not just on the processes, but on the formulae. You want to describe recursive formulae.
That's what I meant to say.
Okay.
Yeah. You can have any predicate with a free variable that is of type the free variable is also of type process predicate, not just a process.
Got it.
Yeah.
Okay. Yeah. All right. Now I'm following.
We're getting everything from namespace logic, and it looks like we might get more. And the question is exactly how much more. Like what can be expressed in this approach and what cannot is probably the main thing that's left to be determined.
That's really awesome. Are you keeping John Baez apprised of the work?
Yeah, he's liking it. That was his main point to emphasize, is that this is going to be some kind of intermediate logic, that it's not clear exactly how expressive it is yet. So he was telling me that I needed to nail that down.
Oh, cool. Very good. Very good.
But yeah, I'm just excited to start meeting with you about how to implement this stuff.
Oh yeah, totally. I'm starting to feel more and more like Agda is missing some key pieces. Like if you want to get the type system involved in the verification of certain properties that are related to the shapes of terms, then reflection is a must-have, because you need to go back and forth between I've got the term as a data structure versus I've got the term as a thing that the compiler can check the structure of. It's looking more like Scala is a better choice than Agda, but I'm gonna still keep contemplating it. But this is kind of my current thinking on the implementation piece.
In those languages, is it pretty straightforward to write down a theory of row calculus?
Well, in Scala, I've given multiple basic implementations where I do exactly that trick of getting the type system to verify that the theory is sound, because the compiler says, yep, this is a type. And yep, this term conforms to that type. So at a minimum, we know it's not trivial, right? The type is inhabited. So yeah, I've given lots of implementations, and I've given exercises to people to try to come up with variants of the implementations. In fact, that was part of the interview process for a little bit in the RChain ecosystem. Handing people these kinds of little puzzles.